Hello, everyone. Welcome to the Bay Area Content Marketing Meetup. We're here today with Floyd Smith. Floyd is co-author of Quantum Computing for Dummies. Floyd is going to talk about what quantum computing is, something I've been trying to learn a little bit about. And he will also discuss the connection between what quantum computing means to us content marketers. Floyd, thanks for joining us, and take it away.
Okay, thank you very much. I'm going to share my screen. I am going to do about 20 minutes of death by PowerPoint with a couple interruptions, and then I'll turn that off and take questions. So I'm going to start by sharing the slides. So here we go, and I'm going to change the view. That's the Zoom view. There's the PowerPoint view, and slideshow. There we go. Okay, great. So I'm speaking today about quantum computing. I got into it through my expertise in book authoring and my general knowledge of tech, not my specific knowledge of quantum computing. So I started out fairly conversant in science and tech, but new to the field in particular. My co-author actually runs a quantum computing company. And so he knows a lot about it, and we did some interviews, and I did a lot of secondary research, and came up with a book that I'm quite proud of. So here's the details of me in the talk. I put my cell phone number in there because the easiest way to reach me is to text me. So please feel free to do that with any questions or follow up afterward. And there is a recording, and the slides and recording will be shared afterward. So no worries about that. I'll convert these slides to a Google Doc and share them online. And just to give us all permission, me permission to be incoherent and you permission to be confused, one of the founders of quantum computing, Dr. Richard Feynman, said, I think I can safely say that nobody understands quantum mechanics, and quantum mechanics is the field that this is all based on. Quantum computing is based on. So I'll go on from there. And it's hard to know what order to explain things in quantum computing. So some questions that you'll have from the early slides will be answered in later slides, but please write down questions you have as we go along so that I can address them at the end. I'm very happy to. Okay, so I've written dummies books. I wrote my first book when I was 25, a published book, and it was in a tech-related field. It was how to use a software program, and another one about the then mighty 80386 processor from Intel that was going to change the world, and it did help. You know, it set a direction that did help. That chip and its successors were actually able to run Windows without crashing too often. So that was actually a big step forward at the time, believe it or not. I was a Mac user then, but I've gone back and forth. I have no loyalty. I'll just use whatever my boss wants me to, or I feel like at the time. And I'm a head of content marketing too, so I speak the same language that we all do and understand why and how to use content to help with sales and marketing efforts. To a certain extent, we all have our areas of expertise. Here's me as the co-author. Rich and Dennis asked me to do this after we had some cocktail party conversation at one of these get-togethers. So please come to the network event, even if, like me, you're sometimes uncomfortable with those things. It's worth it, and it's a really supportive and easy to talk to group. Sales of this book are okay, but what everyone who's like me is hoping for is that the technology they write about has what we call a ChatGPT moment. Interest in ChatGPT just spiked overnight from nothing to huge, you know, within a few days, November of 2022. And if something big happens with quantum computing, hopefully something good for humanity, then we'll see that with quantum computing. And I'm available for casual consulting on quantum computing, like business directional consulting, not how to build one, although I could help you find somebody to build one, but it won't be me with the laser gun. And also content marketing. So I have certain skills. My main skill, actually, and what got me back into content marketing after a break, I really love learning new things, and I'm good at boiling them down to relatively simple explanations. However, quantum mechanics and quantum computing are among the hardest things to explain that anyone's ever thought of. So big challenge, and I enjoy it. I'll start on that today. But let me just set expectations. Usually you have to hear about something a few times before it starts to make sense. So this is like one of those layers. There's never a single aha moment for a complex topic like this one. Just expect the sea level to start rising to where you can have a fairly intelligent conversation. That's a reasonable goal for your first few months of learning about this. So what is quantum computing? And I'm going to get into the magic of it in a few slides, but this is the direct physics explanation, and it's also somewhat historical. So quantum mechanics was invented about 100 years ago, and the first founding event of quantum mechanics was Einstein's equation E equals mc squared. And that means that matter and energy can be interchanged with each other and converted from one to the other. Just note to yourself, how many of you saw the movie Oppenheimer? So I went out on the Barbieheimer night, saw Oppenheimer first to establish my tech cred, but then went to see the Barbie movie with my daughter and granddaughter. And I have to say, Oppenheimer was more satisfying, but I enjoyed the Barbie movie more. So what I don't know what that tells you about me. But quantum mechanics started in the early 1900s, Einstein's equation, and quantum mechanics led to a lot of discoveries in science and technology. So X-rays, lasers, magnetic fields are all that we can manipulate, are all things that come out of quantum mechanics. The atomic bomb and nuclear weapons come out of quantum mechanics. So do satellites, so does the internet, so does your computer, so does the screen on your computer. So many things come out of that work. So why are we just now, more than 100 years later, getting onto quantum computing? Because we can use these earlier generation quantum mechanics technologies to manipulate individual tiny bits of matter. And I'll show an illustration of that and speak to it more soon. But that's the progression, is we needed these more, we were kind of doing quantum mechanics with oven mitts on before. We could only manipulate large numbers of atoms or photons, like a laser beam. There's a lot of photons. So that seems like kind of a miracle to be able to do that, but it's still kind of rough. You then use the laser beam to manipulate an individual photon, and that's where you get to be able to do quantum computing. So we're spoiled for choice, as the Brits say. There are a lot of different particles that you can use as the core of your quantum computer, and we have not yet settled on which one or two we're going to use. So if you remember the early days of personal computing, there were 20 different types of personal computer, and the field got stuck because everyone's energy was divided in 20 directions. And only when we got a couple standards, the Mac and the IBM PC, were we able to make progress. Right now, we're still in that 20 different kinds of PC moment with quantum computers. So that's why we're not moving forward quicker, is we're still doing this research and early development. There's no assembly line with quantum computers rolling off it. Building each of these things is difficult and expensive. And each of these particles, when it's used in a quantum computer, becomes known as a qubit. So a qubit is, for instance, an electron that's trapped in a magnetic field and manipulated by lasers so that it can do a few things that I'll talk about in a minute. But that's what a qubit is it's not the electron itself, it's the electron and all the apparatus around it that allows you to control it. With traditional computers, we have bits, which are 0 or 1. They're little electric switches. So it's almost like a light switch, only at a very tiny scale, tinier and tinier. Qubits are more complicated. There's more going on. We've got to get to where we can manufacture this assemblage, which is, the size of a baseball, into a tiny little thing where you can put millions of them in a box, like a PC box. And what can quantum computing do? Now, I'm not explained yet why quantum computing can do these things. You have to go into this in one order or another. So I'm going to talk about what it can do, and then I'm going to talk a little bit about how it can do it. There are two things that quantum computers do really well, and each of them has a huge number of applications. The first is simulation. So when you start taking electrons and trapping them so that you can manage them with laser beams, and you get a bunch of them, and you get them all talking to each other, then you can simulate what the atoms and molecules in a drug are doing. You can simulate the results of a radiation scan. You can make the radiation scan, you can start to make it much more controlled because you're understanding what's going on. You can build a better battery. So that's the simulation part where you're directly simulating. You have a drug with 97 atoms in it, and you have a computer with 97 qubits in it, and you use the computer to simulate that specific molecule and see what it's going to do in your body when you're ill, right? And these, the quantum computer is not yet powerful enough to do this reliably and usefully, but the people who make drugs are just salivating over what they'll be able to do when they can finally experiment without experimenting on you. They could do the equivalent of a chemical trial, 100 of them in an hour, and really get to new vaccines and so on much quicker. So, oops, I'm sorry. Let me go back. Sorry, I'm messing with my slides. There we go. Some of the other areas are financial modeling. So there's a lot of experimentation in financial modeling. If this person does this and this person does this, what will happen to the stock market tomorrow? So financial modeling is good for this. If I spread my money out in this way or this way, what are my risks? All of those things, all that portfolio modeling and so on, but on a much more complex scale than we do in our, with our 401ks and so on. I'll just mention two other areas. Artificial intelligence. It turns out that both building the models used at the core of ChatGPT, that takes a lot of calculations, is very expensive. It costs millions and millions of dollars to build ChatGPT and specialized computer chips. Some of those calculations can be sped up by quantum computers that we almost know how to build. So that's one of the first things that's going to get better with quantum computing's early days in the next 5 and 7 years is AI. The other one that most people have heard the most about is cybersecurity. Quantum computing has kind of a destructive effect. It can crack the codes that are currently used to protect your financial transactions. It can crack the codes that are used to protect countries' national secrets. So they're building new protective algorithms that will protect this information that won't be able to be cracked by quantum computing. But it's kind of an arms race right now. The protective capability has to get better before the computers get better. There's some nuance to that. We could spend this whole presentation on that, and I'm happy to take a question or two on it. I'll mention one more too. Logistics optimization. If you run an airline and you have 1,000 airplanes, making the best use of those, not putting a plane into maintenance before it breaks down if possible. But once you put that plane in maintenance, that plane was supposed to fly certain routes. So getting that fleet of airplanes to do the right thing every day, or getting all the packages to everybody's house and so on, turns out. I had just mentioned simulation. Some of these areas come from calculation. If you get these qubits vibrating, each of them with many possibilities, and talking to each other, so the combinations all have many possibilities, you can also solve really complex mathematics problems and do things like financial predictions, weather prediction, climate modeling, very valuable things. I'll mention one more example. My favorite example, really, because most people can kind of understand it. If you think of how a battery works, how it gets charged up and then how it discharges, a lot of little specific chemical interactions in absorbing that energy into the battery and discharging that energy back out of the battery. If you can simulate what's going on with those individual crystals in the battery, you can make it work better. And that's very important for climate change, because if we have better batteries, we can store energy when the sun is shining and put it back out when everyone's watching TV and running their AC and cooking in the early evening. So I know that's a lot of stuff in a minute, but this is part of that layering effect, just starting to get into your head some of the things that'll get better with quantum computing. Okay, there's that. There we go. Okay, so now the part I promised about, why is it so powerful? And I've just got a visual to help support this. So what's different with quantum computing? Well, you see that little red ball there in the middle of that image, the biggest one? Okay, so in a typical computer, that's a bit, and it's either, you color it either white or black to show whether it's on or off. and it can only be on or off. It's boring. This red ball with the electrons going around it, it's intended to suggest to you the idea that, say, an individual atom or electron or photon in quantum computing, the reason that you trap it with magnetic fields is that you don't fully fix it into place. You just confine it to an area. And so it's still lively, it's still vibrating, which means that there are actually many possibilities for the specific location of it at any given time. You don't know until you measure it. It's actually theoretically all of those places at once. I'm going to dive into physics for about 3 sentences. Okay, so what's happening in physics is that when you get down to the tiny scale, remember I mentioned that E equals mc squared, so energy and mass change with each other? Well, when you get down to the very small scale, the energy part of that becomes super important. So really, rather than something that you can just hold on to and like I could like bite this with my teeth and leave marks on it, right? That's matter acting as matter. If this suddenly was put inside of an atomic apparatus and converted to energy, it would blow up with the energy of 1,000 suns, you know. So the same pen, the atoms in here have that power in them, but it's all constrained in this nice little package. But if you take an individual atom out of here and you trap it in magnetic fields, it'll vibrate and it'll have a lot of possibilities. That's called superposition. That quality of being able to hold many states at the same time is called superposition. Another thing about, say, an atom, or more to the point, an electron, is that we think of energy as being a wave, right? So we say, okay, there's this much possibility of the electrons here, more possibilities in the middle, and some possibilities way over here. Okay, so and that's the arc of possibilities of where it is. But in reality, in actual reality, an electron will sometimes jump from one side of its curve to the other side. So let's say that there's a barrier in the middle and the electron's over here. Well, if it suddenly goes here, we say it tunneled through the barrier because in our understanding, something can't go through something else. But the electron didn't actually tunnel through anything. It just happened to be on this side in one moment and happened to be on the other in another moment. Sometimes in calculations, getting to the right answer can run into barriers. Like if something's very unlikely, your algorithm doesn't want to go there. But it may be that the right answer to your specific problem is in the very unlikely group. Tunneling can make the answer jump from the mainstream explanation to the new explanation that's actually correct without having to go through the intermediate steps. And I don't expect you to really, like, you can't go do that after this talk. That's advanced math. But that's how it kind of works at a level that we can understand. So that's tunneling. And I haven't even gotten to the best part. Very recent, like in the last year or two, Nobel Prize in Physics was given to people who did work on entanglement. And entanglement is the most mystical and hard to understand part of quantum computing. If you take 2 electrons and run them next to each other so that their wave functions, those 2 waves I talked about, overlap, they synchronize with each other. So if one has a spin in the direction up, the other takes on a spin in the direction down, so that the combination has a net spin of 0 because up sets off, the up offsets the down. So then these electrons go to the opposite end of the universe from each other over a lot of years. And then when you measure the spin of one as being up, you instantly know that some alien somewhere measuring the spin of the other will detect the spin as down. And the fact that you instantly know that, even though there's many light years between you, but there's no time involved in that knowledge, actually is philosophically challenging to our understanding of the nature of reality. Yet, quantum computing takes advantage of that entanglement and is doing so every day. And I'll get to quantum communications in a minute. So this diagram gives you an idea of what's going on in quantum computing. You have these individual electrons or atoms vibrating in a state of superposition controlled by magnetic fields and directed, like made to turn this way and that a little bit by lasers. Then they're connected through entanglement to others. So the number of states that the whole combination of all the electrons that are entangled to each other, and you have a lot of electrons, like let's say you had 1 million of them. the number of states that that can hold is huge, is gigantic. It starts to approximate like the number of atoms in the galaxy kind of number. So you get this thing that can hold all these possibilities as long as you keep it under control. And then the magic of quantum programming is that you make it collapse to the answer you're looking for at a given minute. So send this plane here, send this plane there, send this plane there. And then if some of them hit a storm, do these other things. And that is actually the optimal possible thing you could do with your 100 airplanes coming out of that calculation or simulation of a drug, trying to fight a disease in your body. The answer collapses out as the right answer out of all those possibilities. So that's the magic of quantum computing. The more qubits you get, the more answers you can get. You can start to get answers in seconds rather than centuries. IBM, and this was on 60 Minutes, IBM actually ran a simulation of 17 magnets interacting with each other. And it took them weeks to get them programmed, to get the computer programmed, and so that it simulated the interactions of these 17 magnets, but they were able to calculate details about how those magnets would interact that no supercomputer or set of supercomputers could reach. It would have taken hundreds of years for the supercomputers to get a worse answer than the quantum computer was able to come up with in a couple of days of messing around with it, right? I mean, the actual core work only took a few seconds, but it took them a couple of days to put that answer together out of partial runs of the calculation. So that was too expensive. It took them millions of dollars to get an answer to one question that you might not even actually have, but it showed what the technology will be able to do as we start to manufacture these things at scale. A couple of related technology. Yes.
I'm sorry. This might be a good time to ask this question. My understanding is quantum computing needs to happen at highly low temperatures. Why is that?
Yes, that's a very good question. And it's currently true, although there's some of the work on qubits is to allow those temperatures to be a little higher. The reason is that you see that red ball in the illustration with all that vibration? Okay, if warmth comes along, what is warmth? Well, warmth is molecules moving with a lot of energy. So if there's a bunch of molecules moving with a lot of energy around, if one of them bumps into our friendly guy here in the middle that we're using for calculation, it disrupts it. It's no longer in a state of superposition. It literally, actually, that collision brings it back down to Earth. It makes it ordinary. And so you have to get it embedded in the magnetic field and remanipulated with the lasers so that it's back to that state of like that. So if you make things very cold, you don't get those random collisions that mess up your calculations. And the degree of cold that they really prefer is colder than the chill of deep space, and it's very expensive to. Although actually, I say it's very expensive, but you need like $1 million machine to keep that maintained, and you need to be spending a couple $1,000s a day for the energy to do it. So it's not moon rocket expensive. It's more expensive than you or I would want to pay to do work. So a very good question. So that's where the cryonics part of it comes in. Quantum communications use entanglement to send information that's instant, that's not supposed to be able to happen. So physicists are simultaneously experimenting and tearing their hair out because they shouldn't be able to do what they're doing. And the Chinese government has released some results that they were able to use quantum communications to send information from Earth to a satellite and back to Earth. And they did that to prove, because the distances are so great, that proved that it wasn't some hocus pocus going on, that quantum communications was actually happening. And then quantum sensing, there's all these satellites circling the Earth, and part of what they do is they look at the oceans to see if they can find the other countries' nuclear submarines in the ocean. If you get quantum sensing to work correctly, the ocean just becomes transparent to the satellite, and it can see all the submarines and all the whales and everything else and all the piles of plastic circling around, without any problem. It might have to switch frequencies for the whales versus the submarines versus the plastic, but that's the power that we're looking at getting in the future. from quantum sensing. So these are all related technologies, and they can all work together. Please keep your questions, because this is kind of the peak of the strangeness of the presentation, and I'll go through some of the more practical applications of it in the next few slides, and then take your questions. And all over the map is fine for that. Okay. So what's holding it back? Why are we not doing all this stuff today? Why are we not having, a threat of nuclear war today? Because we can see all the nuclear submarines. Okay, so first is we're still at the stage of experimenting with 5 to 10 different qubit types. That needs to narrow down to PC and Mac. There needs to be 2. Then systems today have from 40 to 400 qubits. I'll show you a graph of that in a minute. And we need systems with millions of qubits. Each quantum computer is custom built. When you had to build your own PC, hardly anyone used them for running a spreadsheet, because most financial nerds were not also tech nerds to go build their own computer, and they had other things to do. I made a little joke here that quantum computers lack error correction, so their calculations are full of errors. And of course, if you're trying to see someone's nuclear submarine, you don't want errors. And if you're trying to design a drug to fight a disease, you can't have errors, right? You can back the errors out by doing a lot of math on conventional computers, but that's very expensive and time consuming. Writing code and algorithms for quantum computers is hard. You actually have to put your mind in the state of how these things work, and then write computer programs in conventional code to manipulate that state, and it's not easy to do. And then this graphic just shows how bad this stuff is in a way. It's a chart that shows the different types of data versus different types of algorithms. And I was already familiar with quantum algorithms versus classical algorithms. I can kind of get my mind into a state where I could sort of see what's going on in a quantum computing algorithm. But then this chart mentions quantum data. And I hadn't really, that's not a big topic of discussion. So I said, I'll go look up quantum data so I can explain it during my presentation. So I look it up, and the first thing I see from a really good source, quantum data defies easy explanation. And then there's a 10-page blog post talking around what quantum data is, not telling you what it is, but kind of, it's sort of like this and it's sort of like that. So this whole field is very confusing and hard to operate on, but getting the right answers is very, very valuable. Okay, so coming back toward the practical with this. This is a graph showing the quantum computers that IBM is building and has already built. And you can see the qubit counts. The idea basically is to double the number of qubits in a quantum computer roughly every year. It's actually taking about 1.5 years, which is a lot slower over time. But these are the computing modules that IBM is building, and they're the leaders in doing this in a couple of different ways. Google does quite a bit as well. You see this Eagle 127 qubits? That's the quantum computing module that was used to do the calculations in the 60 Minutes show that I think it's available on YouTube. I'm not sure. And so they have an Osprey and they have the next one up, but it doesn't actually work that well yet. So, it's just these things are hard. And IBM is actually changing their approach. They're going to start building Eagles, a bunch of Eagles, and then using quantum communications to connect them. They're trying to build instead of trying to build a single thing with more and more qubits in it that are all controlled and manipulated and kept cold, they're trying to build a module that you can manufacture and then have the modules talk to each other so those add up into a bigger quantum computer. Neither is easy to do, but that's more promising. I won't go through the specifics of each of these lines, but as you can see, almost all of these are 5 to 10 years off in the future. All the necessary elements needed to make an industry like the PC industry out of quantum computing. But there's one little thing at the bottom that I'm going to mention in my next few slides. The ability of quantum computers, including hand-built ones, to help with AI and ML is actually closer than most of these other things. And AI and ML are exploding right now. So that's the part, that's where it comes toward us in our work in content marketing. So governments are all over this. They're competing with each other, especially each government wants to be able to read the other guy's secrets, but not have their own secrets be read. And it's scientists who are used to exchanging information freely who are working on this. So you can see the tension. The scientists want to share information to make faster progress, and the governments want them to shut the heck up and not publish anything in order to give that government an advantage. So it's still mostly science-led now. It's still mostly sharing of information, but there's definitely some security agency stuff going on. One of the early boosts to quantum computing is there was a leak, a WikiLeaks type leak, and it turned out that the National Security Information Administration, the NSA, was spending a few $1 million on quantum computing. That made a lot of people pay attention and start to invest in it. And of course, governments they want the economic benefits of the non-secret stuff, of the public stuff. They want people to design better drugs and make better batteries and route their airplanes better and on, right? To predict the weather better. You see with climate change messing up the weather, predicting it better gets more and more valuable. So you want to be able to do that, and you want your country to have the lead in that. So then I'm going to take it to companies and then to people. So what companies will do is some of them are in the business. And, in a group like ours, it may be that none of us ever works for a quantum computing company. Maybe one of them will hire me to tell them why they're not doing a good job of explaining it. That's about as far as I'm going to get. But those are the companies that are actually doing it. And IBM is doing core work in quantum computing. NVIDIA is using conventional hardware to simulate quantum computing hardware. So those are two directions at solving the same problem. This actual article, when I share my slides, this slide is linked to the article. This article is actually a really good 4-page or so explanation of quantum computing. It's as accessible as any I've seen. So good, content marketing by NVIDIA. They're coming into a new field. So how do you make people like you in a positive way? You give them a easy to understand explanation of the field that you're getting into. So it's great content marketing. Here I am recommending it, and I don't know much about NVIDIA. The ones that are more interesting to us, though, like the companies you might want to look to work for, are those that are either coming up with innovations in using quantum computing or the quick ones to apply those to business. So some of you may remember the phrase roadkill on the information superhighway from back around 2000 or so. Quantum computing will have the same thing. In 1984, when the 1984 ad came out, and look it up, it's an important part of computing history if you don't know it, Apple was worth $1 billion and IBM was worth $30 billion, 30 times as much. Today, IBM is worth about $180 billion and Apple is worth over $1 trillion, like $1-2 trillion, depending on how its stock is doing. So that's the difference in which company did a better job of getting in the forefront of technology. And IBM now with quantum computing is trying to reverse that and make Apple the smaller company and themselves the bigger company again. We all saw Amazon really hurt Barnes and Noble. We all saw Netflix literally put Blockbuster out of business. That was all because of the web. And so quantum computing will have similar effects. So even if you don't need to know that much about quantum computing yourself, watch what, get in your head what your company does and see if it's an area that's going to be affected, and then see what your company does about it. Or if you work for a company like a consultancy around around content marketing, see if they get contracts, in more advanced technology areas so they don't get left behind. And then finally, there's not a direct effect of quantum computing, full stop, on content marketing. Some of the problems that quantum computing can solve will affect marketing in general, but there's one big exception, and that's the AI and ML area. We're in the group that's probably most affected of any marketer by AI and ML, that we can and should use it in our daily work. So to me, my recommendation for you guys, really the single phrase recommendation is get an AI tool and force yourself to find uses for it in your daily and weekly work. That's what I'm doing now. And it's not easy because I'm good at doing my job and I can do simple tasks quite quickly. And doing if it takes me an hour of study to do a 5-minute task twice as fast, I just wasted most of an hour. But the 20th and 30th and 40th time I do that 5-minute task twice as fast, I start saving time. So you have to push yourself to make that investment up front, because quantum computing, even if you look at it through a quantum computing lens, the first impact of quantum computing on your work is to speed up that AI model that you can use to do content marketing. So that's my recommendation to you coming out of all this is, even if you don't do quantum computing specifically, be aware it's coming. It's going to speed some things up. One of the first things it's going to speed up is ChatGPT and similar. So that is actually a tool that's very well adapted to use by content marketers. And I will stop sharing my screen and take questions. There we go.
Floyd. We had a question in the chat from Nima. You were talking about daily tasks. What are some examples of using AI for daily tasks?
Right. So in writing an SEO aware blog post about my company's technology, what ChatGPT is really good at is I can ask it to find 10 good blog posts about data architecture, in my case, and summarize them for me and give me their locations. And I can look at the summaries and say, okay, I say to myself, these 3 are the ones that look like the closest fit to what I want to create. So then I go read them, and I can actually ask it, using these 3 blog posts as input, write me an article about data architecture. Now, at the state that it's currently at, I'm not going to edit that article and publish it. What I'm going to do is I'm going to read it. I'm going to write my own that fits our company's style and tone, but I'm going to check it against what ChatGPT produced to see if I'm missing anything. So what happens then is ChatGPT is not doing my work for me. It's helping me do my work faster and better. So the whole exercise takes me 2/3 of the time it would have taken me to do all that searching and everything myself and all that reading myself, and it's actually a better result. So that's an example that I use.
Got it. There was one time last year where I wrote a long article for a client, and it was largely around tips for researching someone's LinkedIn profile to gain insights about that person. And then I decided to put a prompt into ChatGPT to write the same article. And so I compared what I submitted to what ChatGPT produced, and it was scary good. So I wondered, do I have a future in writing? So have you done any experimentation where you've asked ChatGPT to explain quantum computing?
I haven't yet, and I didn't use it to create this presentation because I went so deep pretty recently on the topic that it would have taken me extra time versus saving time and improving the quality of it. So I haven't yet used it. Oh, in fact, a legal issue that I'll bring up for you guys, and I think this is valuable. I wrote my publisher an email at the start of the project. This was at the start of last year when I was starting on the project. I said, I am not going to use ChatGPT or any similar technology in writing this book. And the reason I did that and put it in an email was so that he could be assured that if the copyright wars over ChatGPT went to a bad place, that my book would not be subject to challenge on that basis. Because at the time, and even now, we don't know what's going to happen around ChatGPT generated content. And, the dummies people make millions off these books. They don't want to have any they don't want to hire a lawyer because Floyd used ChatGPT in his quantum computing book. So that's what I was keeping them out of trouble by doing that.
Yeah, I see a lot of marketers who are publishing content where they disclose like where or if Gen AI was used in the content.
Yes. So what I did was I created a paper trail. And what I did effectively, I'm going to use a legal term, I indemnified my publisher. Because if I guarantee to them that I'm not doing something, they can rely on that. So even if I'm lying, it's on me, not them. So their lawyer says, our hands are clean, go sue Floyd. And everybody laughs because that's not going to get them too far. Yes.
Okay, here's a good one from Brian Piper. Oh, did someone speak?
I did.
Oh,
Going back to that scenario, if you write something that's your own work and you put it in Chat GPT to revise or to clarify, would that be subject to any type of legal issues?
Um, we don't know. We don't know yet. We just know from previous examples, it's almost as obscure as quantum computing, what's going to happen with the law around ChatGPT. However, what usually happens is that a company like OpenAI, the makers of ChatGPT, ends up doing a settlement with large organizations like the New York Times, like Reddit, like all these others, where they basically end up kicking back some of their revenues back to those companies. So it probably won't affect us individual users.
Thanks.
so Floyd, a good one here from Brian Piper. Hey, Brian. Will quantum computing help us make the leap to artificial general intelligence?
There are, so probably is the one word answer. The only caveat there is that there are philosophical reasons why quantum computing actually shouldn't work. And we're finding in the labs that those philosophical rationales don't hold up and that we can do quantum computing. But there are also philosophical reasons for believing that you can't achieve artificial general intelligence in this reality. And only continued demonstrated progress in the field will prove those philosophical concerns to be right or wrong.
Got it. We have time for one or two more questions. Anyone have a question? Feel free to put it in the chat or to come off mute and ask it. So Floyd, you were talking about you have to think about the underlying how quantum computing works if you are to program to use it. Are people working on some, like essentially the compiler, like taking code and then getting it onto the quantum computing hardware?
Oh yes, there's a lot of work on that.
Okay.
I'll point out as a cautionary example, a lot of people have spent a lot of time and effort on no code and low code tools.
Yeah.
It turns out that in order to do something that looks like programming, you have to be able to think like a programmer. So even if you don't know a specific programming language, you still have to have that rigor of thought and focus. And so similarly with quantum computer programming, they may make the tools easier to use, but you still have to do some pretty unusual thinking in order to make it do interesting stuff. But that doesn't affect us. We're mostly just a bit downstream, looking for the results of the work, just as in AI. Some of us are adopting the work early. None of us probably on this call are doing AI research ourselves.
Got it. Excellent. Well, thanks so much, Floyd. Everyone stick around because we're about to do the big book giveaway. I'm going to close this out for the recording. So Floyd, thanks so much for joining us. And everyone go check out, where is like Amazon, or is it in actual bookstores, Quantum Computing for Dummies?
It is, and my preferences are, so my personal preference and my authorial preference is that you buy it from Amazon and then post a review, please, because reviews are gold. And my personal preference is I like to read quote unquote audiobooks, and it's on Audible as well.
Oh, it's on. Excellent. All right. Thanks so much, Floyd.
Mm-hmm.